Written in Bone Chapter 3, Out of the Grave, J.R. 1225b's bones were so fragile that they had to be removed from his grave with the supporting soil of the pedestals still beneath them. Otherwise, they would have crumbled to bits. With the soil still in place, the bones were carefully transferred onto trays and sent for conservation, a treatment process to protect them from decay and damage. Although archaeologists may begin this process while the bones are in situ, Kelso's team felt that conserving JR 1225b's bones in the lab would be easier. This process took place at the Jamestown Rediscovery Project's conservation laboratory near the excavation site. First, senior conservator Michael Lavin set aside several untreated bone samples to send to Owsley for scientific analysis that require bone material that has not been conserved. Using soft brushes, dental picks, and especially treated water, Lavin removed all traces of the soil that clung to JR 1225b's bones. The next step, drying the skeleton, took a remarkable 2 weeks. Although the skeletal material may appear dry within hours, it still retains some moisture, Lavin stated. This hidden moisture must be removed gradually to prevent the bones from shrinking, such as they had in the grave after heavy rains. Lavin further explained that conservation experts solved this problem by placing the bones in drying racks and conserving them with plastic perforated with small holes. The holes controlled the amount of air that reaches the bones, slowing the drying process. Next, Lavin coated the bones with an acrylic mixture that acts like glue, binding the bones tightly to prevent breakage or flaking. After the mixture dried, he fitted together fragments of broken bones and glued them as well. Finally, he wrapped JR 1225b's labeled conserved bones with a clear plastic material specially made for protecting fragile items and placed them in storage boxes to prevent damage from changes in the atmosphere. The boxes were kept in a temperature controlled and humidity controlled vault until they were sent to Owsley's forensic laboratory at the Smithsonian Institution. There, Owsley and his colleague, Carrie Brulhide, a skeletal biologist and forensic anthropologist, laid the skeleton on a table, each bone in its anatomically correct position. Using a magnifying lens, they examined each bone and tooth and made notes of their observations. Next, Owsley and Brulhide used precise measuring tools called calipers to measure JR 1225b's long bones. These measurements are compared with those that were made in situ to confirm their accuracy. By plugging these measurements into a mathematical formula, they determined the teenager's height was about 5 feet 8 inches, unusually tall for the 17th century, and he was still growing. After the measurements were taken, the forensic anthropologist set aside additional bone and tooth samples for laboratory tests. The scientists turned their attention to the femur next to which the arrowhead had been found. Close examination confirmed Owsley's initial opinion at the gravesite. The arrowhead had not penetrated or damaged the femur in any visible way. That still left the possibility the wound had become infected and had led to blood poisoning, which would have killed the boy without causing any damage to the bone. Forensic examination of a different bone, the boy's right clavicle or collarbone, provided another clue. The clavicle had been fractured. Its broken edges hadn't healed at all, indicating that the break must have occurred shortly before the boy died. This injury helps explain why the boy's right arm and shoulder had slid into such an awkward, abnormal position as he was placed in his grave. The shoulder could slide into that position only because the clavicle was broken. Together, the arrow wound and the broken clavicle led Owsley and Brulhide to conclude that the boy had likely died as a result of violence. The boy had other health issues too. A depression in the front of his skull above his left eye socket revealed that he had sustained a blow to the head that had healed before his death. The bone in the roofs of his eye sockets contained small holes, a sign that his diet lacked sufficient iron, and x-rays of the boy's legs bones showed band called Harris lines, which form when the growth of a bone repeatedly stops and restarts. Such disruptions of growth are a result of poor nutrition or the stress of disease. The most serious problem by far, however, was a raging, ongoing infection in the boy's lower jaw, where two central incisors were damaged. The left incisors was broken in half, exposing the pulp, the soft inner part of a tooth that contains the nerves and blood vessels. At first, the injury would have caused intense pain, particularly at mealtimes, because the exposed pulp chamber would have been extremely sensitive to cold and heat. The boy probably covered the broken tooth with his lower lip and tongue to protect the exposed nerve from hot and cold foods. Within 10 days, as the pulp deteriorated, a pus filled area called an abscess formed as the tooth's root. After a week or two, the nerve of the tooth died, ending the pain the boy felt from hot and cold substances. The problem hadn't gone away, though. Osley saw signs that the abscess spread, further inflaming the bone socket and the surrounding gum tissue. During a period of several months, bacteria and infections spread into the bone of the boy's chin and jaw. Once the infection had spread that far, JR1225B would have been in severe pain again, possibly worse than before. Left unchecked, the infection would have affected his immune system. Colonial people often died from infection that modern antibiotic medicines can cure. Depending on the type of bacteria involved, the severity of JR1225B's infection would have soon caused him to die. It's likely that the boy's sudden death as a result of the arrowhead wound only shortened his life by a few months, if not weeks. If the Jamestown teenager were alive today, his broken tooth would have been treated. An endodontist, a dentist who specializes in disease of the tooth pulp, will drill the nerve out of the broken tooth's root and pack the empty root canal with the filling material. Modern painkillers make this procedure far less excruciating than the suffering JR1225B endured. Finally, a dentist will replace the top part of the broken tooth with a false crown made of a tooth-colored porcelain-like material. Within days, the boy would have been enjoying his meals without any problem. He ate like an Englishman. One kind of laboratory test critical to forensic anthropology is called stable isotope analysis. Stable isotope analysis can supply information about a person's diet. In the case of some colonial settlers, provide clues to the settler's birthplace and how long he or she had lived in America. The stories gleaned from laboratory examinations and tests are detailed, fascinating, and sometimes shocking. The next fact that JR1225B's bones revealed came via a chemical element called carbon. When green plants undergo the nutrient making process of photosynthesis, they absorb varying amounts of three forms or isotopes of this element: carbon 12, carbon 13, and carbon 14. Carbon 12 has 6 protons and 6 neutrons in the nucleus of each atom. Carbon 13 has 6 protons and 7 neutrons, and carbon 14 contains 6 protons and 8 neutrons. Carbon 12 and carbon 13 are called stable isotopes because they do not break down over time, as carbon 14 does. All three isotopes are absorbed by bones when people consume green plants. Carbon 13 is of particular interest to forensic anthropologists for two reasons. First, the amount of carbon 13 that bones absorb varies depending on the type of plants a person eats. Second, as a stable isotope, carbon 13 remains in a person's bones after death and can be measured even centuries later. These two characteristics enable scientists to determine what plants the person ate, and sometimes based on where those plants commonly grow where the person lived. In colonial Chesapeake studies, the key plant is corn, which grows in many parts of North America and contains more carbon 13 than many other grains. Corn played a significant part in the diets of Native Americans and colonists. Before their arrival in North America, however, the colonists would have eaten grains that were commonly grown in Europe: barley, wheat, and rye, for example, which contains a much lower amount of carbon 13. As a person's diet changes, the nutrients that the body transports to the bones reflect the new foods. Over time, the bones themselves change. For example, when people born in England moved to the American colonies and started to eat more corn, the level of carbon 13 in their bones slowly increased. Scientists think that it takes about 20 years for a bone's carbon 13 content to be completely replaced by dietary change. The amount of carbon 13 found in bones can be measured and analyzed based on scientific research to determine a number known as carbon 13 value. This value is written as a negative number, that is, a number less than zero. A person born and raised in England, for example, typically has a carbon 13 level with a value between negative 21 and negative 18. The carbon 13 value for a person born and raised in North America on a diet that included corn would be in the range of negative 15 to negative 9. Scientists believe that a value between negative 18 and negative 16 in the colonial Americans remains indicate that the colonist was probably born and raised in England and immigrated to North America, where he or she lived less than 20 years before death. The isotope analysis of the samples taken from JR1225B's bones revealed a carbon 13 value of negative 19.3. The value of negative 19.3 is very English, with absolutely no corn influencing his diet. Brouillard's note because the amount of carbon 13 in the boy's bones is so low, Ousley and Brouillard are confident that he had only recently arrived from England when he died. The isotope analysis fits perfectly with JR's 1225's identity as a boy likely in service to one or more of the men, or a ship's boy who was killed shortly after arriving in Virginia. Brule Hyde added, in fact, he may have been a victim of a documented Indian attack on James Fort that took place on May 25, 1607. One colonial document which describes this attack mentions that a boy was killed. The historical evidence uncovered so far supports this theory. Catherine Carroll Walls volunteers as a historian for the Association for the Preservation of Virginia Antiquities. One of her goals is to identify JR1225B by researching the historical record. At least 4 boys were known to have been on the 3 ships that arrived in Jamestown in 1607 and were therefore likely candidates. Reading journals, church records, and many other materials, Cora Walls meticulously traced leads for each name. 2 of the boys are mentioned as being alive in journal accounts in 1608, so they clearly hadn't died in 1607. According to records found in England, the 3rd boy would have been 9 years old that year, too young to be JR1225B. The last, and Cora Walls believes most likely candidate, is a young man named Richard Mouton. Richard Mouton is listed by John Smith as one of the boys that arrived in Virginia in May of 1607. His name does not appear again in the records, she explained. We have not determined the exact birthplace or birth date for Richard, but I have located one possibility in a baptism record for 2nd of June of 1593 in London, England. Richard Mouton certainly seems a fitting candidate for JR1225B. His disappearance from the historical records suggests he may have died in 1607. If Carroll Walls has correctly located his birth record, he was 14 years old at the time of his death, well within Doug Ousley's age estimate for JR1225B. Still, as tantalizing as the possibility seems, JR1225B may not be Richard Mouton. Many colonists who traveled to Jamestown were not listed in the historical records, so the skeleton could belong to an unnamed boy. Only further research will determine whether the identification can be confirmed.